A simple linear regression is basically this formula where y equals b0 plus 1 times x, and you might recognize this formula from back in high school. It's just a formula where a trend line or a slope line on a xy axis, and let's go through these variables and coefficients one by one. So this is the dependent variable. The dependent variable is something you're trying to explain. For instance, how does a person's salary change with the years of experience that he has? So in that case, y would be the dependent variable, or what grade does the student get depending on how much time is put into studying. In that case, y would be the dependent variable. So something that you're trying to understand how it depends on something else. X is your independent variable. In this case, in a simple linear regression, we only have one independent, and we don't even have to call it x1. We could just call it x, and this is the variable that is you're assuming that is causing the dependent variable to change, or as we will learn further, sometimes that independent variable might not be a direct cause and effect, but still there might be an implied association between the two, and in that case, you're trying to figure out this association. Then B1 is coefficient for the independent variable. And it kind of says how the effect or how a change in x1, a unit change in x1, and we'll be talking about this a lot, unit changes. A unit change in x1, how that affects a unit change in y. So it's kind of, think of it as the translator or the multiplier, something like that connects the two, the connector between y and x1. So you can't just say, you can't always say x1 is directly proportional. There is, well, you can't just say y, the change in x is always equal to the change in y. There might be this coefficient of proportion to which proportion that change is inflated or deflated, and b0 is a constant, so it's a constant term. And we'll talk about constant. Let's look at the simple linear regression because it's easiest and it's pretty straightforward. You can visualize it. Here we've got the y and x axis. Let's look at the specific example where we have experience and salary. So experience is going to be our horizontal axis and salary our vertical. And we want to understand how salary depends on their experience. Well, what we do in regression, we don't come up with a theory. Look at the evidence. We look at the the live facts and observations we had. So in a certain company, this is how salaries are distributed among people who have different levels of experience. And what a regression does is, so that's the formula for regression. In our case, it will change to salary equals b0 plus b1 times experience. And this means it is putting a line through your chart that best fits this data, and look uh, uh, and it even looked like it. So it's quite hard to draw a line that fits this data better. And the assumption here is it's impossible. This is the best line that approximates this data. For now, let's focus on the coefficients and the constant. What is constant? Well, the constant actually means the point where the line crosses the vertical axis. And let's say it's $30,000. What does it mean? Well, it means that when experience is zero, as you see on the horizontal axis, when experience is at zero, then in the formula on the right, you can see that the second part, B1 times experience becomes zero. Salary becomes B0. That means that salary will equal to $30,000 when a person has no experience. So as somebody is fresh from university and joins the company, most likely we have a salary about $30,000. There's some confidence intervals there, but we don't go into that. Just we can say that according to this model, that person will be probably getting paid $30,000. Now, what is B1? That is a slope of the line. And so the steeper the line, the more you get, more money you get per extra year of experience. Let's look at this example. Let's say somebody went from maybe 4 to 5 years of experience. So then to understand how his salary will increase, you have to project this into the line, then project that onto the salary axis. You can see that Here, for 1 year experience, the person will get an extra $10,000 on top of his salary. So if the coefficient B1 is less, then the slope will be less, and that means the salary increase will be less per every year of experience. If the slope is greater than that, means the experience will yield the more increase in salary. And that's pretty much it. That's how a simple linear regression works. So the core goal here is that we're not just drawing a line theoretically that we came up with somehow. We're actually using observations that we have to find the best fitting line. In the, we talk about linear regression being the trend line that fits your data. Now we'll find out how to find the best fitting line, or how the simple linear finds that line for you. Here's our simple linear regression. The same chart, salary versus experience. We've got these red dots, which represent the actual observations that we have in our data. And we've got the trend line, which represents the best fitting line or the simple linear regression model. So now let's draw some vertical lines from the actual observations to the model, and let's look at one of the specific examples to understand what we're talking about here. Here you can see that the red cross is where that person is sitting at in terms of salary. So let's say this person with 10 years of experience is earning $100,000. The model line, so the black line at the bottom, is it actually tells us where that person should be sitting according to the model terms of salary. And according to the model, it should be a bit lower. It should be somewhere where that green cross is, which is about maybe let's say $80,000. So now the red cross is called YI. So Y of the subscript I, and that is the actual duration. The green cross is called YI hat, and that is the modeled observation or the modeled value. So basically, with that level of experience, where would he be? Where does the model predict that he would be earning? And so the green line, therefore, is the difference between what he's actually earning and what he should be earning. What is modeled to be earning. So therefore, the green line, it will be the same regardless of what dependent variable you have, whether it's salary or it's grade at school, whatever. So it's the difference between the observed and the modeled for that level of independent variable. Now, to get this best fitting line, what is done is you take the sum, you take each one of those green lines or those distances, you square them, and then you take the sum of those squares. Once you have the sum of the squares, you gotta find the minimum. So basically, what a simple linear regression does is it draws lots and lots of these lines, these trend lines. This is like a simplistic way of imagining it. The linear regression draws all possible trend lines through your data and counts the sum of those squares every single time. And it records it somewhere in a temporary file or something, and then it finds the minimum one. So it looks for the minimum sum of squares. It finds the line which has the smallest sum of squares possible, and that line will be the best fitting line, and that is called the ordinary least squares method. Multiple linear regression, same thing, but many variables. So B, 0, 1, constant, and then many combinations or many pairs of B and X, and it can go up to quite a lot. Depends on how many regressions you have. Here, once again, you got a dependent variable Y, something you are explaining, but this time the difference is that you think there might be a few causation here. So in the case of salary, for instance, it could be how many years of experience you've done, how many other courses you've done, how much time you spend at work, or things like that, or how valuable, how much money you make for the company in terms of a student and his grade. So if your independent variable is what grade does the student get, then the independent variables could be how much the student has studied for the exam, maybe how much he has slept before the exam, how many lectures he has attended throughout the course, and things like logistic regression intuition. There's some very interesting slides coming up, and this is quite an important topic, but at the same time, it is quite challenging. So, a quick heads up, there will be some math, and I've done a few run throughs of this presentation already, and we'll try our best to convey everything in the simplest way possible. So let's get into it. We already know about the linear regression. We know that there's a simple linear regression that has this very short formula of one independent variable. And we also have looked into the multiple linear regression, which has many independent variables. We know how to deal with this type of challenge with when we have a scale put like that, where on the horizontal axis we've got the independent variable, on the vertical axis we've got the dependent variable. And this is an example at salary versus experience. How do we create a model here? We use a simple linear regression. It puts a line through our data, and that line is modeling our observations. So we can basically forecast things and compare our actual observations to our model and so on. But so we know how to deal with challenges like that or problems like that. But your company had hired you as a data scientist, for example, what they do is they send out email of first customers with like a proposal to buy certain products, might be a clothing store, a grocery store or something. So what they do is they send out an offer in email to a lot of customers to purchase some product. And here you've got a sample of those customers that they contacted recently. You've got their age, and you also have a variable whether not they took action or not. So, did the person take up an action, perform an action? Did they take up an offer? Did they buy a product, open up an email, respond to the email, and so on? What action are taken? And very black and white, very different. But at the same time, like even though we don't know what to do, we don't know what's going on here. Not what it's not what we're expecting, but at the same time, intuitively, we can see that there is some sort of correlation. Can see the observations on the bottom, they're a bit more to the left. Observations on the top are a bit more to the right, implying kind of older people are more likely to take action based on this offer, and younger people are more likely to ignore it. So how can we model this? How about we try the existing method in our uh, which we will try linear regression. It doesn't look like the best approach, but let's see. Doesn't look the best method to solve this problem. Let's look into this in a bit more detail. We're going to draw the other horizontal line over here instead of trying to predict exactly what's going to happen for any given person. Let's imagine a person, and let's say we want to predict for that person, knowing their age, we want to predict whether they will take up the offer or not. But instead of predicting exactly what they're going to take it up or not, how about instead we will predict the probability? We'll stage a probability or a likelihood of that person taking up that offer. And if you think of it in that way, right away things start becoming clear. You can see that, okay, so this chart is actually from 0 to 1. And I also know that probabilities are from 0 to 1. So basically, you could feed in probabilities between 0 and 1. The fact that the red dots, the red observations are already either 0 or 1 and nowhere in between. We already know that they're either there or but for something we're predicting, it kind of makes sense to say we don't know for sure. We don't know 100% we will take it up or not, but maybe of an 80% chance he will take it. If you think of that way, linear regression, or at least that part that in the middle between 0 and 1, it makes sense. Or there in that part, because basically it's telling you that anybody between those ages of, for instance, where it's crossing the horizontal line for the first time, or where it's crossing the horizontal axis, it might be like 25, or let's say 25, 35. And where it's crossing the horizontal axis for one, it might be, let's say, 55. So those people between 35 and 55, any person that falls in between that age, there's a probability of them taking up the offer. and the probability is increasing as we move to the right. So we take more and more older people, that probability is increasing. The part of the linear regression in the middle kind of makes sense and we can do something with it, but the parts that don't make sense at all are the ones at the top or bottom, because the probability can never be less than zero or it can never be above one. So what's the linear regression trying to give us a hint about here is that, or what we could interpret is that people above that age, that we said 55, above that age, they're very, very likely to take offer actually more than 100%. They're definitely taking it up. Anybody below 35 on the other side, on the left, they're definitely not taking it. So essentially what we're saying is we ever take that approach, we would have to replace this linear regression line for a line that looks like that, cut those bits of and replace them with horizontal parts, and that would be a very basic, but it still would be an attempt to at creating a model for this situation. We would still be able to use this to make some sort of predictions and assumptions that talk about the correlation between the action and the age of a person. So that's a very basic understanding, and that's kind of the start of our understanding of intuition behind logistic regression. So let's see what the actual scientific approach is. So here we've got the line that we looked at, and it's described by this equation. This part is gonna be, uh, if you apply to this equation a sigmoid function, which looks like that, you put the y into the sigmoid function in purple, and then you solve for y from the purple box, and you put y back into the blue box, then you will get the green box. So basically, your linear regression will start to look like this, and this is the formula for logistic regression. And what we'll do to your chart, which is most importantly, this visual part, it will convert it from the chart, which is actually the logistic regression function. So if at this stage you're asking yourself what just happened, then the first time we saw this and learned about this was the expression. If you're totally comfortable for all that, that's super great. That means you'll thrive through this section. But if you're confused right now, not a problem. Let's take this step by step. Let's look at it step by step, or exactly what happened. So there's one graph, our graph. There's independent variable, our outcome, yes or no. So that's the y, the dependent variable. And there are our observations in our data set. Based on these observations and plus using this formula, which we're going to take as given, this is the logistic regression formula. Using this formula and these observations, we come up with the line, and and what's important to understand here is not a magical line. This line for the logistic regression is the same as a slope or a trend line for linear regression. So what this line is doing is it is using the formula, it's following the formula, and it's the best fitting line that can fit these data sets. We're doing exactly the same thing as of for linear regression, but it just looks different. So there are hips of these lines that you can draw that look like that, but only one of them is the best fitting line. So the point here is to find the best fitting line, and this is it. We found the best fitting line that follows that equation and fits these variables that we had in our data set. After that, we can forget about the equation. We forget about the variables. We've got our line. This is our logistic regression function. We found the same thing as of for linear regression. We've created the model. You can see it. This is the model in front of you right there. Now, what we can do with this logistic regression, we can use it to predict probabilities, and we've already touched on probabilities. They lie between 0 and 1, and that's instead of predicting for sure something will or will not happen, we predict probability. Probability, however, is called p hat. That the little sign above that P hat, and anything you see with the hat is the section just basically means something we're predicting. So that's a way to remember it. That picture P hat. So we're predicting this probability. Let's take four random values for the independent variable. For X, we're going to say 20, 30, 40, 50. Let's see what happens to these variables. Let's put them on the X line. Those are the dots, and we put dots, not X or crosses, because it doesn't mean that they're on the horizontal bottom line, doesn't mean that their probability is zero, that their dependent variable is zero. They're just there because they're on the x-axis. We plot them there. What you need to do, find the probabilities, is you need to project these values onto your curve. Once you project them, you get these blue dots or blue observations, which plotted basically. So these are the fitted values. As you remember, in red, you have the actual, and in blue, you have the fitted values. These are your fitted values. And now if you project them, if you want the probabilities, you need to project them to the left like that. And let's have a look at these probabilities. The person who is 20 years old, the probability of taking this offer is very low, 0.7% perhaps, so less than 1 percentage to take up this offer. The person who is 30 years old, the probability is higher. It's about 23% to take up the offer. Person who is 40 years old, probability is 85% according to this model. And the person 50 years old, probability is 99.4%. That's what we can get out of a logistic regression. That's what we're going to be using. We're going to be using it very actively when we're talking about building geodemographic segmentations and using probability as you score. And we'll talk about this more. So we actually rank people most likeliest to take up with least likeliest. It's actually even better that you having a 1 or a 0 probability, so you can order people by this probability. Because it's a regression, we want a prediction for the y value. We can get y the actual. We can't get the actual because the actual is something we can only observe in our data set or in real life. Can only get the prediction for the actual. Y hat, as the hat suggests, is the predicted value for the dependent variable. How do you get Y hat? The approach is very arbitrary. You have to select a line. So you have to select a line. We're going to select 50%. You can select it anywhere, but 50% is usually selected in the middle. Therefore, you have symmetry, and anything below this line, so anything that falls in the curve below the line will be projected downwards onto the zero line, which makes sense. Basically saying if your probability, your predicted probability of taking up this offer is less than 50%, let's say 40 or 20, then we're just gonna say that you're probably not gonna take up this offer. And that's what is happening. The person with 0.7%, with whatever it was when 723, the probability are not zero, but they're below 50. So if you do require a y hat, so a predicted value, yes or no value, then makes sense. You're probably gonna say that they're not gonna take up the offer. There you go. Both of them y hats are zero. Anything above the horizontal line that we selected, the 50% line, is agreed that all of those values that fall onto the curve above that line are projected upwards. They're projected onto the yes line, the one line. So the person that had a probability of 85 is projected outwards. The person had a probability of 99.7 is projected upwards. If you're predicting that somebody's probability of taking up an offer is 85%, then if you have to say yes or no, then you're probably gonna say yes. You're gonna say yes, this person would take up the offer if you have to choose one of the two. So those are our predicted y hat values. If in this case, they're both one of those two variables, and those are the two things you can get out of the logistic regression. So you get the probabilities which are important. Also, you can get the y hats, the predicted values for the dependent variables. Once again, it's important to think of it as it's doing exactly the same thing as a linear regression. It's fitting the line even though it's not a straight line. And the values are not scattered. Everything looks bizarre in its uniformity or in its structure makes it look bizarre, but still it's pretty much the same way. We've agreed on the line or a formula for the curve, and we're trying to fit the best curve to our data. Once we've done that, we've got the model. We've got the coefficients, which we'll talk about in the next discussions, and we can start drawing conclusions or insights from this model. And some of the insights are we can get the probability of somebody taking action or of the event occurring, or basically of the answer being yes. So it's not a yes or no, it's a probability. So 85 or 20%. So that's when we project it to the left onto the y-axis. We can get a predicted value for the dependent variable based on where we select this arbitrary line, 50%. You can select it anywhere you like. You can select it higher, lower, depends on your knowledge about the problem at hand and as you understand, depending on where you selected. And that will significantly affect your variables. So I really hope that this explanation was trivial enough and yet insightful enough for you to gain an intuitive understanding of logistic regression. That and